We talked about the titration of strong acids and strong bases last week. So just a quick review here. This is the pH curve for the titration of a strong acid with a strong base. We start out at an acidic, a low pH. The pH jumps very fast. The equivalence point is right in the middle of that. And then at the end, it tapers off again. So before the equivalence point, we have an acidic solution. After, we have a basic solution because now we have an excess of hydroxide. When we titrate a strong base with a strong acid, the curve is similar to sort of flipped, right? So now we start with a high pH, we get the equivalence point, the pH drops rapidly, and then we end up with an excess of acid afterwards. So this is the example we didn't do last week, so we're going to do this one. A 50 milliliter sample of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of nitric acid. So anytime we're adding something, we need to think about, well, what reaction is going to occur? What's the stoichiometry? So we're going to do a stoichiometry calculation first. So we've got sodium hydroxide being added to nitric acid. And that's going to react, and it's going to form sodium nitrate and water. And we don't actually care about those products, but there they are. So we're looking at moles initial, the change, and moles after, or millimoles initial and millimoles after. So 50 milliliters of 0.2 molar sodium hydroxide. Just a quick review. 50 milliliters times 0.200 moles per liter. That can also be written as millimoles per milliliter. The calculator part of my brain is not turned on yet, so I'm going to use an actual calculator. Yeah, 10. So this gives us 10, and that's millimoles. So I'm not going to write that out again, but we do those calculations over and over and over again. So you take milliliters, you multiply by the molarity, you get millimoles. Okay? So here, for the sodium hydroxide, we start with 10 millimoles. And then we are adding 60 milliliters of nitric acid. So 60 times 0.2. And again, my brain is not turned on yet. 12 millimoles. So we're looking at the amount in moles or millimoles that have been mixed together, and then we're going to see, well, which of these is smaller? The smaller one is going to get all used up. That'll be the limiting reactant. So the smaller one is going to be the change. So all of this is going to go away. So we subtract 10 from that, and we subtract 10 from this. And we end up with 0 and 2. Wow. Now, if we care about the other side, which here we don't, we start with 0 of that, and we're adding 10. So we end up with 10 millimoles of sodium nitrate, but and water never matters. It doesn't do anything. Because this is strong acid, strong base. There's no equilibrium going on. We're going to get to that very soon. So we have 2 millimoles of nitric acid. Nitric acid is a strong acid. Nitric acid. Strong acids ionize completely. So this means that we have 2.00 millimoles of hydrogen ions in the solution. Everybody okay with that? We need the concentration to find the pH. I'll try that again. We have moles, millimoles. We're going to divide by milliliters. The volume has changed a lot, actually. We started with 50 milliliters, and we added 60 milliliters. Millimoles divided by milliliters gives us molarity back. So I've got 2 divided by the quantity 50 plus 60. 0.01818, repeating. We are asked to find the pH. pH is the negative log of the hydrogen ion concentration. Negative log of 0.01818. .7404. So the pH will be 1.74 at this point in the titration. Any questions? Pardon me?
The hydroxide, the sodium hydroxide is in the beaker or in the...
For this one, the sodium hydroxide is in the flask, and the nitric acid is in the burette. So we're adding the nitric acid. Tiger?
Yeah, I was just wondering
Where are the 12? Okay, great question. So that comes from 60 times 0.2. Okay? So I wrote this one out because I think everybody needs a refresher on that. 50 milliliters times 0.2. The units work out this way. Moles per liter can also be written as millimoles per milliliter. So we take this and we multiply by milliliters and we get millimoles. So we can always just take whatever milliliters are given, multiply by the concentration, and get the millimoles for our stoichiometry table. And most of the time, we're not going to bother to write that down. But thank you for asking, because I'm sure somebody else wondered where that came from as well. Any other questions? It's really important to understand this before we get into the weak acids and bases, because that's going to add another layer. So we need to be firm on this. Any questions? Okay. 1.74. And then here's just a sort of a conceptual question. So we have a strong acid in the flask, and it's represented, the concentration is represented by the little circles. Those are the hydrogen ions. And we have a strong base in the burette, and that concentration is represented by the little hydroxide molecules here. So it's asking which mark on the burette indicates the amount of base required to reach the equivalence point. So equivalence point is where we have equivalent amounts, right? That's where all of the H plus is going to get reacted with OH minus. So how many do we have in here? 1, 2, 3, 4, 5, 6, 7. This is the sort of math you do in OChem, counting, usually not more than 10. So if there's 7 in here, then we need 7 of these guys, right? 1, 2, 3, 4, 5, 6, 7. Oops. Yeah, well, there it is, 7. That makes sense? This is a good, I like this slide because this is what we need to be able to picture in our minds. We can't see any of this happening. But I have this place I call Mrs. K's Chemistry Land. The happiest place on earth? Well, maybe. But it's in my mind like a big whiteboard, except it's like three-dimensional and animated. And so I make pictures of this stuff in my mind. I imagine the things coming together, and that helps me to remember and to understand what's happening. Because if you're just looking at letters on a page, it doesn't make any sense, right? It just doesn't. Okay. Weak acid with a strong base. So here we're going to titrate 25 milliliters of HCHO2. How do we know this is a weak acid? It's not strong. It's not one of the six. If it's not one of the six, it's weak. We don't need to know what its name is. There it is. That's a weak acid. We're titrating it with sodium hydroxide. I suppose you could titrate with a weak base, but we're never going to do that in Chem 1A. That would be just icky. I don't know why you would want to do that. So here we're trying to find the volume of sodium hydroxide required to reach the equivalence point. So here we have an important statement at the bottom. The volume at the equivalence point depends only on the amount, the moles of acid, not on the strength. So whether we're doing equivalence point volume for a strong acid or for a weak acid, the calculation is exactly the same. And this is the kind of calculation that we did in Chem 1A. So let's just run through this fairly quickly. I'm going to take the information that I'm given up here and write it under the chemical equation. So I have 25 milliliters of the weak acid, and I'm told that the concentration is 0.100 moles per liter. And remember, that is the same as millimoles per milliliter. And then I have sodium hydroxide, also 0.1 molar, 0.100 moles per liter, millimoles, milliliters. I'm trying to find the volume of NaOH, so question mark, milliliters. They don't say milliliters, but that would be convenient. So this is a stoichiometry calculation. And so what I teach my students is you always start, let's leave some room, with grams to moles to moles to grams. It's grams to moles to moles to grams, grams to moles to moles to grams. That's the starting point. That's not what we always end up using, but we can take the starting point and modify it for what we need. So we ask ourselves, well, am I starting with a mass of compound? No, I'm starting with milliliters. Remember, in dimensional analysis, the starting unit is usually just a single unit, and anything that has something per something is usually a conversion factor. So I'm starting with milliliters, and what am I ending up with? Also milliliters. So instead of going milliliters to moles, let's do millimoles. Any questions about how I fix that up? We're looking at, well, what are we actually starting with? What are we actually ending up with? And let's find a nice path. Milliliters to millimoles to millimoles to milliliters. And this always reminds me of Dora the Explorer. You guys watch that show at all when you were kids? Dora, Dora, Dora the Explorer. Who do we call when we don't know which way to go? The map, right? And map comes out of the backpack, dances around, and then we look at the map, and then they chant, right? You know, it's like, well, first, we're starting in the snowy mountains, and then we have to go over the scary bridge and through the spooky forest or whatever. And then they repeat it, right? So this is Dora and the map first we start with milliliters, and then we go to millimoles, and then to the other millimoles, and then to the milliliters. We say it 3 times so that we remember which way we're going. This is the map, this is the path, this is what tells us what to do. You don't absolutely have to write this down. You're not beginning chemistry students anymore, but you might still find it helpful. So we take that, and we're starting with milliliters. Starting with milliliters of this guy, 25 milliliters of HCHO2, and then we're going to millimoles of HCHO2, and then we're going to a different millimoles of sodium hydroxide, and then milliliters of sodium hydroxide. So I took the path here and wrote it down. And I just added some identity here. Milliliters to millimoles to millimoles to milliliters. Then I need units to cancel out, so I'll take this milliliters and bring it down here. Those cancel out. I don't want to scare you too much, but the final exam for this class is the ACS chemistry exam, and it includes questions from Chem 1A. So there will be like stoichiometry problems. Just heads up. Got all the units in place, and now I'm looking for numbers. So millimoles to milliliter of HCHO2. Well, that's this guy, and there's my concentration, right? And I never leave enough room, 0.100. I often leave enough room on the wrong side. And then what's the relationship between millimoles of sodium hydroxide and millimoles of weak acid? It's 1 to 1. It's the stoichiometry here. Most of the time we're going to see 1 to 1, but every once in a while, not. So this is 1 to 1. And then at the end, we have milliliters and millimoles of sodium hydroxide. Well, that is the molarity again. It's just upside down. But 0.1 goes with millimoles. So again, I don't have enough room. It goes down there. And then you can stick 1s in here if it bothers you that there's no numbers. Well, even with my foggy morning brain, I can tell that this is 25 milliliters of sodium hydroxide because the 0.1s also cancel out. This calculation is exactly the same as titrating a strong acid. Any questions? I think I probably gave you way too much detail there, but whatever, right? Come on, advance the slide. There we go. Yeah. Okay. So, like with a strong acid, we're going to find the pH of that acid solution before we add anything. So we have a weak acid, and so this is going to be an equilibrium problem. The weak acid will ionize partially, forming H3O plus and CHO2 minus. And so we're going to look at an ice table. We're going to look at our initial concentrations, the change, and the equilibrium. So initially, we have 0.1 molar HCHO2. So we put that in here. Remember, ice tables use molarity. Stoichiometry tables use moles. We're saying there's essentially 0 hydronium and none of the conjugate base. So then we look at the change. Well, this one's going to go down, minus X, and these will each go up, plus X. So we add those rows together, 0.1 minus X, X, and X. Now we need the Ka, and that was given to us here So the Ka, Ka is 1.8 times 10 to the minus 4. And that is the products divided by the reactants. So that's going to be x squared divided by 0.100 minus x. Two ways to find out what x is. Use the solver on your calculator, or use the x is small approximation. Use whichever one is easier for you. I'm going to do x is small because just I've got a lot of practice doing that, so it's easy. So x is going to be the square root of this times 0.1, and I get 0.004243. Anybody do that on a solver?
Not 0.004153.
4153? Anybody else? Same? Okay. So that's a little different, right? We should, of course, always check that this is actually small. Take that number, divide it by 0.1, multiply by 100. So this one's on the edge. It's 4%, but it is still small. So this is the solver, and this is x is small. The solver always works. Yeah, feel free to, I forgot to bring the calculators down if you need one. So then we want the pH, right? X is equal to the hydronium ion concentration. So the pH is going to be the negative log of X. One 1.3724, 1.37. Let's see what we get with the solver number, 0.004153. Yeah, it's 2. When I typed it in, I left out a 0. Thank you. I did the other one and I'm like, wait, that's not even close. What's going on? So using the value from the solver, I get 2.38. Any questions? So this is a calculation we learned how to do in the previous chapter. Okay, now things will get interesting. So we're going to add 5 milliliters of sodium hydroxide to our weak acid and calculate the pH. So for weak acids, the strong base is going to convert a stoichiometric amount of acid into the conjugate base. And now we have weak acid and conjugate base. The solution is a buffer. So then we can use the Henderson-Hasselbalch equation, which makes things go a little faster. So here is our stoichiometry table for adding the sodium hydroxide. So I'm adding sodium hydroxide to the weak acid, and that's going to make H2O and the conjugate base. So moles initial, I'm going to take my 25 milliliters times 0.1, and that's going to give me 2.5 millimoles. I'm going to take the 5 times 0.1, and that's where I get my 0.5 millimoles. We're starting out with 0 of the conjugate base. So we have a limiting reactant problem. We're going to look at the one that's smaller. The smaller amount is the change. So minus 0.5, this will give us 0. This one also minus 0.5, we get 2.00. And on the product side is plus 0.5. So now we have 0.5 millimoles. You see what happened? What we're doing every time we do a calculation, we just calculated the pH of the solution, but we're not going to start with those amounts and add sodium hydroxide because that's going to be harder. We're always going to start with, well, this much of that, we know it's going to ionize, but let's just think about the starting things first, and then we'll worry about the equilibrium. So this is a buffer, right? 2 millimoles, 0.5 millimoles. Wait a minute. Hang on. So we can use the Henderson-Hasselbalch equation here. pH is equal to pKa plus the log of the base divided by the acid. We can use this equation with millimoles or moles instead of molarity because the volumes are the same and they will cancel out. If you don't feel comfortable doing that, go ahead and calculate the concentrations. We will end up with the same answer. So we need the pKa. We aren't given the pKa. Well, we have Ka. Remember that P means negative log of. So this is the negative log of 1.8 times 10 to the minus 4. .7447. So 3.7447 plus the log of the base. What's this guy? It's a 0.5 divided by the acid. .1427, 3.14. Any questions? Adding the strong base, I'm going to assume that all of the base reacts with my weak acid. That's what this table is doing. We're going to react all the hydroxide, use it all up, and see what we have left of our weak acid and how much conjugate base gets formed. We have amounts for both of these. It's a buffer solution. We can use the Henderson-Hasselbalch equation. Any questions? How do we know when it's a buffer? That's an excellent question. When we have amounts of the weak acid and its conjugate base. We have both of them here.
And the one before we were having also we were having in there.
Yeah, so in this example, we have an initial amount. Here, we don't know how much is going to be the base. you're correct. We do have some conjugate base, and we have the weak acid, so why isn't this a buffer solution? Well, I guess technically you could say that it might be, but because this ionizes so little, the amount of this that forms is very small. It's not really going to function as a buffer. But more practically speaking, in order to use the Henderson-Hasselbalch equation, we need a number for this, right? We need a number here, and we need a number there, and we don't have that, so we can't do that. Does that make sense? That's a great insight. Okay, so we plotted the pH here. We keep adding 10, 12 and a half, 15, 20 milliliters of sodium hydroxide. These numbers come from making a stoichiometry table and looking at how things react. And we have amounts for the weak acid and the conjugate base, and so again, we can use the Henderson-Hasselbalch equation to calculate the pH. So the same process we just did with different numbers. This is a table I forgot to change. I overlooked it. So here the amounts are in moles. If these were in millimoles, we'd have 1.5, 1.25, 1.00, and 0.50. That would be the millimoles. Which numbers are easier to deal with? The millimoles. I mean, because you saw in the last example where I typed a number like this with 2 zeros in front to do the pH, and I screwed it up. So I only put in 1 0 instead of 2. So the first slide on this example, we calculated the volume needed at the equivalence point, and it was 25, right? 12 and a half is half of that. So that's called the half equivalence point. At the half equivalence point, the moles of the weak acid and its conjugate base are equal because half of the acid is converted into the base. So let's just do this real quick here for the 12 and a half. The pH is going to be that 3.74, whatever it was, plus the log of the base, divided by acid. The acid and base concentrations, amounts, are equal, and so that's 0. The pH is equal to the pKa. We're just looking at this one. So that's a shortcut. If you are looking for the pH at the half equivalence point, you don't have to do a calculation. The pH is equal to the pKa. It's also a way that you can discover what the pKa of an acid is you measure the pH at the equivalence point, and then that tells you what the pKa is. Any questions? Okay, let's look at the equivalence point. So after the equivalence point, we don't have a buffer anymore because we will have used up all of the weak acid. So here we're adding 2.5 millimoles of the base to 2.5 millimoles of the acid. These are equal, and so we get 0 and 0 and 2.5 millimoles of the CHO2. We can't use the Henderson-Hasselbalch equation because this one is 0. It's not a base anymore. What we have now is just the weak base. So we're going to use an ice table, but we can't do it for the acid, we have to do it for the base, because all the acid got converted into the base. So we look at what that base does. The base will ionize or react partially to recreate the acid, making hydroxide ions. And so we can look at the initial here. What did we do? So the 2.5 millimoles is the amount of the weak base at the equivalence point. And for the ice table, we need concentrations. So we have to divide by the new volume, which is the initial volume plus the volume added. So that gives us 50, and we get 0.0500 molar of the weak base. At this point, it's the same kind of calculation as from chapter 17. We say we'll start out with 0 of this and approximately 0 of that. This goes down minus x, these go up plus x. We add those together and we get expressions here for equilibrium. So this is a base. Kb is equal to HCHO2 times hydroxide divided by CHO2 minus. So that's equal to x squared over 0.05 minus x. But what is Kb? They didn't give it to us, and they're never going to give it to you because it's supposed to be simple enough to calculate. Ka times Kb equals Kw. So Kb equals 1 times 10 to the minus 14 divided by Ka. .5556 times 10 to the negative 11. We have to calculate Kb and use Kb in this ice table. So again, we can solve this one of two ways. Use x is small or use the solver on your calculator. I'm going to do x is small. I'm going to take that Kb and multiply it by 0.05 and take the square root. What does x is small? What does the solver give us? The same? How do we calculate the pH? Can we just take the negative log of x? Does x represent the hydrogen ion concentration? It's the OH concentration. So this is on the opposite side of the pH, circle of pH. You could go either way. I'm not especially fond of doing these sorts of calculations. I think subtracting from 14 is simpler. So I'm going to calculate the POH. This is the hydroxide ion concentration. long ago. This is a lot of steps. How are you supposed to remember how to do this for an exam? Because there definitely could be a question like this on an exam. There are different variations of these problems, and so you can't just memorize a formula or even really a set of steps. We have to be able to think about what's happening and do those calculations. So we need to be able to do the stoichiometry calculation. We need to be able to convert millimoles to volume using the new volume that's added, so we need to be able to calculate that. We need to be able to do an ice table. We need to be able to calculate Kb from Ka and know when to use Kb, right? If we have a base here, we use Kb. If this is the acid and we're making H+, then we use Ka. So we have to fill out the ice table, get this equation and solve it, and then we have to recognize what is X. X is hydroxide. So how do I get from hydroxide ion concentration to pH? My preferred way is to calculate pOH and then calculate pH from that. We have done all of these pieces, right, in class this semester. But this is the first time we've strung so many of them together. You are not going to just instantly remember how to do this. So how do you remember? You practice. So what I recommend doing is, as soon as you conveniently can, go back to these problems and just looking at the original slide, just looking at that, do the calculation. You're probably going to get stuck the first time you try. Then either go to your notes or go to the video and just watch enough that you're like, oh, I see what I need to do now. It's just like a little hint. And then do as much as you can. If you get stuck again, watch a little more of the video. That's what I think the videos are probably the best for, is just a little guided practice on your own. And so then you get through it, well, start over and try to do it again. Any questions? So that was the pH at the equivalence point. And this was on a previous slide, I didn't mention it. The pH at the equivalence point for the titration of a weak acid is always basic. If it's a strong acid, strong base, it'll be pH 7. But for a weak acid, it will be higher than that. So here, after adding 30 milliliters of sodium hydroxide, now we've gone past the equivalence point. We're doing our stoichiometry table. So hydroxide 30 times 0.1 gives us 3, and 25 times 0.1 gives us 2.5. We look at which of these is the smaller. Now it's the acid that's smaller. So all the acid gets used up, and that one is 0. Not all the hydroxide gets used up. So these are both minus 2.5. This is plus 2.5. I just have to do this. So what do we do now? We have a solution of hydroxide and weak base. We need to do an ice table for the weak base. So we've got our weak base, CH O2 minus. In water, will be in equilibrium with the acid and hydroxide. Initial change, equilibrium. Well, CHO2 minus, that's 2.5 millimoles. Divided by the new total volume. 25 milliliters plus 30 milliliters. Zero point 0.04545. What's the initial concentration for HCHO2? It's 0 divided by that. What's the initial concentration for hydroxide? It is not 0. It is 0.5 millimoles divided by this. 0.5 divided by 25 plus 30. Point 0.009090. I think I actually made this mistake in lecture yesterday. I forgot to write this in. I just used 0 and we came up with a wrong answer. And then we caught it fairly quickly, thankfully. This is not 0 anymore, so there's a concentration here. So then we look at the change. This will be minus x plus x plus x. And we do not have enough space, so we will make some space up here. Magic. You've got margins on your printed notes. KB is the HCHO2 times hydroxide divided by the CHO2 minus. We calculated KB already. So this, I don't remember that number, but I found it in my calculator. So 1.667 times 10 to the minus 6 is equal to the products, x times that. Oh, 2 zeros, watch out for that. It is 10 to the minus 14 over Ka.
5.5
Oh, did I do that wrong?
times 10 minus.
Okay, thank you. I was trying to be fast and just find it. 5.556
Yeah,
times 10 to the minus 11. Yeah, that sounds better. Thank you for catching that. And that will be divided by 0.04545 minus x. Again, use your solver or use x is small. Bless you. X is very, very, very small here. So I think your solver will give you pretty much exactly the same answer. What does X represent? No, it's not the OH minus. That's an easy mistake to make because usually X is the H plus or the OH minus, and we just take the negative log of it and we're mostly good to go. But the hydroxide ion concentration is 0.009090 plus X. If X is small, do we actually have to add it on? No, we don't. But if you don't remember that, go ahead and add it on. You'll get the same number. No harm done, right? So the hydroxide ion concentration is is 0.009090 plus X, which is 009090. And then we find the POH. So the negative log of 0.009090. There's just not enough room. So you can calculate POH is 2.0414. And then the pH is 14 minus the POH. I'm just going to round it here, 11.96. That's a messy one, isn't it? We look at the dot that's graphed here, it's very close to 12, so that helps me to believe that I did that correctly. And let's see if I can fix this. Any questions? Again, this is a lot. And this one had one little extra thing compared to the previous one, right? When we find X, it's not the hydroxide ion concentration. So the same process there could be done for 35, 40, and 50 milliliters. And then you'll get these pHs. So that's something else you could try at home. Pick one of these and do it. See if you can get the right pH. So our overall pH curve looks very similar. We start in the acid range and is sort of flat-ish, and then it goes up and then it's sort of flattish afterwards in its basic. So we need to be able to calculate the pH at any of these places. So the initial pH, that's just a solution of a weak acid. So that one's fairly straightforward. Before the equivalence point, the weak acid solution is a buffer because we've transformed some of the acid into the conjugate base. And so in this buffer range, we can use Henderson-Hasselbalch and not have an ice table. In the equivalence point, this is where things start getting a little murky, right? So here, we're going to have all of the acid converted to the base. So then what we have is a solution of the conjugate weak base, or weak conjugate base, and so we need Kb, and we need an ice table. Afterwards, this is nice and flat, but this is not a buffer. So we can't use Henderson-Hasselbalch. We're going to do the stoichiometry. We're going to find out that we have extra hydroxide, and then we will have an ice table for that weak conjugate base. These are the messy ones. Any questions? Yeah. How do you know when you're at each point? That's a great question. Well, the first point is easy because you haven't added anything. You need to do the stoichiometry table at each step. So when you're in this area, you're going to see that you have both weak acid and conjugate base. So let's see if it actually shows on one of the slides. Yeah, so if we do the stoichiometry, here I've got an amount for the acid and for the weak base, buffer. So no matter what these amounts are, as long as you have a non-zero number there, you're going to have a buffer solution. When you do the stoichiometry table at the equivalence point, you're going to end up with both of these reactants being zero. And so that's how you know that you're at the equivalence point. Because a problem on a test is not going to tell you that that's the equivalence point. But you make your stoichiometry table and you find these out, and now, oh, I've got a solution of a weak base. Yes?
So how do we know at the equivalence point?
We know it's the equivalence point because when we do this table, we end up with these being both zero. The moles or millimoles of the hydroxide is equal to the millimoles of the acid. That's the definition of equivalence point. And then after the equivalence point, you're going to end up with moles of the weak base and moles of hydroxide. And so that's also a weak base calculation, but it's just a little ickier. Does that help? Yeah. Because if you don't know where you are, it's hard to know what to do. Any other questions? So this would be a nice exam question. A 40 ml sample of 0.1 molar nitrous acid is titrated with 0.2 molar potassium hydroxide. Calculate the pH at the equivalence point. They give us Ka. We need to recognize that this is a weak acid. So if, we've memorized our strong acids, this looks like HNO3, but it's not. The other big clue is they give us a Ka. Strong acids don't have Kas. They're essentially infinite. So this is a weak acid. So what do we have to do in these titration curves? Yeah, here, we're not given the volume, right? We're not given the volume of the KOH.
Is it the volume equal or the concentration equal at the equivalent?
At the equivalence point, the moles are equal. Yeah. So the first thing we have to do is calculate what is that volume. So HNO2, I almost wrote 3. This is the reaction that's occurring, right? The nitrous acid and the potassium hydroxide. So this is a Chem 1A calculation. So I have 40 milliliters of the acid, and it's 0.1 molar, and the hydroxide is 0.2 molar, and I don't know what the volume is. So grams to moles to moles to grams, but we're starting with milliliters and ending with milliliters, and it'll be easier if we do millimoles in the middle. So 40 milliliters of HNO2, and it's 0.1 millimoles of HNO2 per 1 milliliter. Then we're going to convert to millimoles of the KOH. And then milliliters of the KOH. So I kind of jumped ahead here and stuck that unit in the bottom. Milliliters to millimoles to millimoles to milliliters. I'm going to have a mole ratio here in the middle. That comes from the stoichiometry of the reaction. And then at the end, I'm also going to use the molarity, 0.2 moles per liter, or 0.2 millimoles per milliliter. Oops. $20 milliliters of KOH.
The 20 milliliters is the volume of
KOH.
in the burette.
It's the volume of KOH in the burette that we have added to the flask. Yeah. The burette is designed to measure how much liquid has been released from it. We never know exactly how much is actually in the burette because there's that unaccounted for volume down where the tip is. And that's something that I think a lot of Chem 1A students don't quite understand. We're not concerned with how much is in the burette. We're concerned with how much did we put into the flask. And the burette is designed to measure what we've released. So this question is similar to one we did earlier, but it's not exactly the same, right? Because we didn't tell you what the volume was. Make you calculate it. And that's why you can't just memorize a pattern. Sorry. But life isn't like that either, right? You can't just memorize a pattern in life and follow it and have it always work. Sure would be nice, but... Okay, now what do we do?
Get the moles, take the pH.
Well, we can't take the POH yet because this is just telling us how much KOH we added. So we have done stoichiometry here, but is this a stoichiometry table? No, we need to do a stoichiometry table. the MICMA thing, right? So what I'm going to do is I'm going to erase this part. Everybody have that written down? No, I didn't grab all of it. Got most of it. So I need to look at moles initial, the change, and moles after. So we did the earlier calculation and found out that we're dealing with 20 milliliters of added KOH. So millimoles of nitrous acid, 40 times 0.1. How many millimoles of KOH? 20 times 0.2. This tells me I did my calculation correctly, because this is the equivalence point where we have equal amounts of acid and base. So the change is going to be -4. So these are going to be 0. Change over here is +4. I'm tired of drawing all the lines in the tables. So this is what happens at the equivalence point. The concentrations here, the amounts are 0 because they reacted with each other. And now we have 4 millimoles of NO2 minus. That is the weak base. Because if we get rid of that spectator ion, then maybe it's a little easier to see. This is the hydroxide, and that's the weak base. We need to calculate the concentration of the weak base. We've got 4 millimoles, and we divide by the volume. So the concentration of the NO2 minus is going to equal 4 millimoles divided by the total volume. We started with 40, we added 20. Now what do we do? Ice, ice, baby. In these pH curve calculations, the only time you're not going to have an ice table for weak acids is in that buffer region. You'll need one for the initial pH, you'll need one at equivalence, you'll need one after the equivalence point. So we need an ice table. So we're looking at, I'm going to change color here. So I've done orange. So we also got that number on a solver, and I'll just give you kind of a tip here. In the pH calculations for titration that we're going to do in this class, X is always going to be small. it's always going to be small. That's not something we'll try to trick you with. If it's not a pH curve titration or a titration curve calculation, then all bets are off, right? It could be X is not small, but for the titration ones, X is going to be small. What does X equal? The hydroxide ion concentration. As I was grading the exam, I was just looking through the scratch paper, and a lot of you are not making ice tables. They're really, really helpful. So, POH is the negative log of X. The negative log of X, 5.9194. pH, 14 minus that. H 0.0806, 8.08. Any questions? I'm just going to skip one. I don't like that example. What if we're titrating a weak base with a strong acid? The calculations are really similar. We're going to start. Our initial will be a solution of a weak base. At the half equivalence point, we have the base and conjugate acid concentrations being equal. We'll see an equivalence point, and then it will go to acid. Now, this is a buffer region, just like for the weak acid, but the Henderson-Hasselbalch equation has pKa in it, because we're calculating pH, not POH. So we're going to use pKa for the conjugate acid of the base. Like, that's not confusing. What's the pH at the half equivalence point in the titration of a weak base with a strong acid? pKb of the weak base is 8.75. So we're titrating a weak base instead of a weak acid. But the half equivalence point is a magical place. At half equivalence, pH equals pKa for acids and bases. They didn't give us pKa. This is pKb, right? It's 14 minus, yeah. So it's just 14 minus that, which gives us 5.25. So pKa plus pKb equals 14, just like pH plus POH equals 14. This 14 is because we're in an aqueous solution at room temperature. That's the equilibrium constant for water. Any questions? Polyprotic acid, you can see why we're not getting past this section today. So let's look at H2SO3. So this is a weak acid. The hydrogens come off one at a time. So first it'll lose one hydrogen to give us HSO3 minus, which is the conjugate base of this, but also acts as an acid. And HSO3 minus can lose another hydrogen to give us SO3 2 minus. So there's a Ka for each of these. If those Kas are sufficiently different, then the pH curve is going to have 2 distinct equivalence points. There's not many acids that'll do that, but you could get that. So at the first equivalence point, you have to add enough base to equal the concentration of the original acid. That'll react all of this. And then to get to the second equivalence point, you need to add the same amount to take care of the second one. So the volume needed from one to the other is equal. Oops. So questions like this on an exam are going to test whether you understand the ideas without making you do all the icky calculations. So consider these 3 titrations. I'm not going to read them out loud. I'm just going to look for what's different about the choices. The volumes are the same. The concentrations are the same. We're titrating with the same concentration of the same thing. The thing that's different is we have a monoprotic weak acid, a diprotic weak acid, and a strong acid. So those are our choices. Which statement is most likely to be true? All 3 titrations have the same initial pH. Is that true? I saw one. No? No, that's not true. If these were all strong acids, it wouldn't matter which acid they were. They would have the same initial pH. Weak acids and strong acids are going to have different pHs because it depends on the Ka, right? And monoprotic and diprotic are going to be different as well. All 3 titrations have the same pH at their first equivalence points. What's the pH of a strong acid at its equivalence point? 7. It's neutral. You react all the acid with all the hydroxide, and now basically you have salt water. So that one's going to be 7. Weak acids, we can't just give a number, but is it going to be 7 or above 7 or below 7? It's going to be above 7. The equivalence point for the titration of a weak acid is basic. So that's not true. All 3 titrations require the same volume of sodium hydroxide to reach their first equivalence points. Is that true? Yeah. Because the volumes and concentrations are all the same. The monoprotic acid and the diprotic acid, to completely titrate this, you're going to need more, but it's talking about the first equivalence point. Depending on how your brain works, questions like these are harder or easier than all the calculations. Shoot, I forgot it. I keep forgetting there's just more. This is the section that never ends. It's almost done now. So we can monitor the titration with a pH meter or with an indicator. So indicators are what we used in Chem 1A. For the indicator, we're going to be looking at an endpoint. So the endpoint is where the indicator changes color. And if we choose our indicator correctly, that endpoint should be at or very close to the equivalence point. So this is a titration with phenolphthalein. In acid, phenolphthalein is colorless. As we get in here, we're just where it is changing from colorless to pink. And so we see just a little bit of color. And then when we go past the equivalence point, we see the dark color. So indicators are weak organic acids that have a different color than their conjugate base. And they have very intense colors, so you only need a little tiny bit. So when we use phenolphthalein, you're putting in like 2 or 3 drops of a 0.1% solution. So it's very, very little. we wouldn't want to have to add a lot because these are also weak acids, and so we don't want to be titrating them. This is the structure for phenolphthalein. You know, the name is kind of a mouthful, but we definitely don't want to draw that out. This is the colorless acidic version, and this is the pink basic version. And you can see that the color is changing right around here, 8 to 9. So the indicators change color within a range of 2 pH units centered on their pKa. So their pKa plus or minus 1, that is the region of changing, and that's where they're going to be useful as an indicator. So if we are at the pKa, we're going to have an intermediate color because we've got half of each. If we are above, we're going to have the basic, and if we're below, we're going to have the acidic. And so this is showing, I think this is methyl red. Yeah, methyl red. It says it right there. Showing how the pH changes from 2 to 4, 5, 7, 9. And so the pH for this one is, I'm guessing, around 7. And so we're going to see that color change in there. So this is a table of a whole bunch of different acid-base indicators. There are 2 that are diprotic, so can be used at 2 different pHs. How do we choose our indicator? You want to know what is the pH at the equivalence point for my titration. So phenolphthalein is what we used in Chem 1A. For weak acids, we were titrating acetic acid, citric acid, oxalic acid. They're all weak acids. So this one is changing color like around 8.5 to 9.5. And for the titration of a weak acid, the pH is going to be basic. And so this is a good one. If you have something where your color is changing, you want a lower pH, phenolphthalein isn't going to work for you.